So from now on, it's going to be a science talk. This is an overview of the recommendations that we have for carbohydrate intake during exercise. And I'm going to show you some of the studies that we've done that have resulted in these recommendations. But first, I'm going to explain to you what this graph shows. On the horizontal axis, you can see the duration of exercise here from 1 hour, 2 hours, 3 hours to longer. On the vertical axis, you can see like the amounts of carbohydrates. So initially, if the exercise, for example, here is between 1 and 2 hours, we recommend an intake around 30 grams per hour. If it's between 2 and 3, 60 grams an hour. And then if it's longer than 3 hours or maybe even 2.5 hours, you should consider 90 grams an hour. That's a lot of carbohydrate. And especially when we first started to do this research and athletes were taking maybe at best 20 to 25 grams of carbohydrate per hour, even in a Tour de France, for example. Like when you then suggest, well, maybe instead of the 25 grams per hour, you should take 90 grams an hour, everyone thought that I was crazy. So what we'll talk about is like, how did we get to this? And where does the 90 grams an hour, where does that come from? And in order to achieve that, what should the products look like? This is like a really sort of classical study. As you can see that the year it was published was 1986, long time ago, but it showed that if you take carbohydrate during exercise, that it helps you to maintain your blood glucose. If you just ingest water or a placebo, your blood sugar goes down. And after a while, it goes down to such low levels that you start to feel lightheaded, very well known as bonking. And of course, that is a disaster for your performance. This is why in this study, they couldn't exercise longer than 3 hours, 180 minutes. But with carbohydrate, they could go an hour longer, or maybe they stopped it. Maybe they could have gone even longer. So that's, we know that carbohydrate feeding works during prolonged exercise. There are many, many studies that show this. And the reason it works is that you maintain the use of carbohydrate as a fuel. You can see that here. With carbohydrate, you can maintain it. Without carbohydrates, you cannot use enough carbohydrate. That means at some point, the power has to be reduced. There's another, and I'm just going to go through this really quickly, another really interesting finding that we, a long time ago, also in 1997, we did a study where we compared a carbohydrate drink versus placebo. And we asked cyclists to ride 40 kilometers as fast as possible. And before we did the study, my assumption was, well, 40 kilometers is really short. Your body stores of carbohydrate are going to be so large that you're never going to run out in 1 hour. So there shouldn't be any effect of a carbohydrate drink if you take it during that time trial. But we were surprised to find that with the carbohydrate drink, these cyclists were 1 minute faster. The problem was we couldn't explain why. So the next study we designed, we actually infused it directly into the blood. We infused glucose directly into the blood. We compared it with a placebo infusion, saline infusion. And this time, even though we delivered the same or even more carbohydrate, it had no effect on performance. We then designed the third study because that didn't make a whole lot of sense. In the third study, we gave these cyclists a carbohydrate mouth rinse. So they got the same carbohydrate drink, but they were asked not to swallow the drink. So they would just rinse their mouth with it, and then they would spit out this carbohydrate drink. And this time, we found the same 1 minute improvement in 40 kilometer time trial performance. So what that tells us is, because we infused it, it didn't make a difference. It has nothing to do with delivering energy. But when we mouth rinse and there are receptors in the mouth that detect the carbohydrate and send a signal to the brain, that is the reason why performance may be improved. Now, since then, we have lots of studies, and you can see them all listed here. If these bars are going to the right, it means there was an improvement in performance with a carbohydrate mouth rinse. If they're going to the left, then there was a negative effect. But these effects are not significant. And here you can see lots of studies show that a mouth rinse, just rinsing your mouth with carbohydrate without swallowing any of it, it also works, at least during like higher intensity, shorter duration exercise. And the reason it works is that there is a central effect on the brain. Normally, when we exercise, it starts in the brain. In the brain, we send a signal to the muscle, and the muscle starts working. When the muscle gets tired, it sends signals back to the brain. And it's telling your brain, well, now you have to stop because I'm getting really tired. And your brain tries to tell the muscle, just keep going as long as you can. But at some point, there's so much negative feedback coming into the brain that you fatigue. What we think happens is if you mouth rinse with a carbohydrate solution, then somehow that interferes with all this negative feedback that's coming from your muscle and makes you think, actually, I feel quite good. That is the story for like really high intensity exercise. So carbohydrate works, but it works for a different reason than just providing fuel. In this case, or in longer exercise, it really is about fuel. We store it in the muscle. We have 400 to 900 grams of carbohydrate in the muscle. How much there is depends on how much muscle you have. It also depends on your diet. If you eat a lot of carbohydrate, you can store more. If you have a lot of muscle, you can store more. There's also 60 to 90 grams stored in the liver. That's quite important, but it's a small amount. And then we can deliver carbohydrate through the intestine, of course, when we ingest it during the activity. Now at rest, we only use about 7 grams in an hour. But during exercise, we may use as much as 350 grams in 1 hour, huge amounts. So you can see that very rapidly you would get rid of all of your carbohydrate stores. We also know that if you take carbohydrate during exercise, the more you take, the more your body will use and the more your performance will improve. So that's what this slide shows here. So what we try to do is, like, how can you deliver as much carbohydrate as possible? And the technique we use is a technique where we label the carbohydrate. What that means is a carbohydrate has its name from the word carbon, and it's made out of, like glucose, for example, is made out of 6 carbons. And we can label that carbon by replacing the normal weight carbon with a heavier weight carbon. Normal weight is 12, 13C is the heavier carbon. Now we can measure that weight of the carbon in the carbohydrate. So if we give a drink here that is labeled with this carbon 13, the drink or the carbohydrate gets digested, it gets absorbed, it gets oxidized in the muscle. And then you exhale the carbon as carbon dioxide. In that carbon dioxide that you exhale, you can measure the carbon 13 again. So if we measure how much carbon 13 we're ingesting, we measure how much is in the expired gases, and we measure the total CO2 production, then we know exactly how much of the carbohydrate that we ingested was utilized. Yeah, so it's a very accurate technique to measure how much of the carbohydrate that is in your sports drink or your gel is actually used during exercise. And what you get is something like this. This is 2 hours of exercise, 120 minutes. And we call that exogenous carbohydrate oxidation. So that is how much of your carbohydrate in your drink or gel is used. And if that is glucose, you can see that it increases the first 60 to 90 minutes and then it levels off. And in this case, it is just over 0.8 grams per minute. Those values will become important in a minute. If we compare that to galactose, another carbohydrate, then you can see that glucose values are much higher here. So I would conclude from that, I would rather have a glucose drink than a galactose drink. Okay? We can then compare different types of carbohydrates. These are just images of different types of carbohydrate that you could have in your drink. The most common ones are maltodextrin, and then glucose and fructose. But even starches like this molecule here could be used in a sports drink. If we look at all the studies and we plot how much of a carbohydrate is used during exercise versus how much was ingested, then you get this figure. And roughly you should see this pattern. Initially, when we ingest more, your body uses more. But there is a limit to how much your body can use. If you ingest more than roughly 60 grams of carbohydrate per hour, it doesn't further increase the use of that carbohydrate. So what's the point of taking more than 60 grams an hour? And at that time, this was a publication in the year 2000. At that time, the recommendation was do not take more than 60 grams an hour. But we were curious and we wanted to find out why can your body not use more than 60 grams of carbohydrate per hour? Is this because she cannot ingest more? No. Is it because it's sitting in the stomach? We tested that. The answer was no. Is it because you cannot absorb more? The textbooks were telling us that your capacity to absorb carbohydrate is unlimited. Is it because the liver plays a very important role and maybe stores all this carbohydrate so that you cannot use it in the muscle? We ruled that out as well. And we know from studies where we infused glucose, that your muscle can take up way more than 1 gram per minute and also use more than 1 gram per minute. So we had to question the textbooks, and maybe the textbooks were wrong, and maybe absorption is a limiting factor.